Okay, hello everyone. This is the second part of our Math 2521 2621 seminar. I am Ronald, and I'll be presenting the first part, and then the rest is going to be presented by Bruce Chen. So yeah, I'm just going to be doing Cauchy integral formula and Cauchy's generalized integral formula. So let's get started. So initially, we went through Cauchy-Gaussat theorem, right? That's essentially if we have a closed contour and the function that we had was holomorphic on and inside the contour, then we would be able to just say that it was equal to 0, right? Oops. So we also saw an example where it was not holomorphic everywhere, but it was holomorphic some point here, right? So since it was out here, it wasn't actually on or inside the contour that we were integrating along. So Cauchy-Gaussat theorem still applied. But what if we have the case where there is some point inside the contour where it's maybe not defined or not differentiable, not holomorphic? Well, we are able to use Cauchy's integral formula, which basically says if we have some holomorphic function divided by some linear term, then the integral, if it's integrated along a closed simple contour, is going to be equal to 2 pi I multiplied by the function value at w, where w is where what we would call a singularity would occur, which is just the point where it's not differentiable. So let's apply it. What you might notice here is that in our Cauchy integral formula, we actually only have one linear term at the bottom, but this question has two. So a common way to deal with that is just to use partial fractions, where instead we have two different terms. Each of them have a holomorphic function at the top, but they both have a singular linear term at the bottom, which means that we can individually apply Cauchy integral formula. So let's do that. We have the integral, and of course we know that a circle of radius 3, that's obviously both simple and closed, so we can integrate across it. And then we've transformed it such that each individual function that we're doing is some holomorphic function divided by a linear term, and so we can use Cauchy integral formula. And so we choose our f of z to be e to the power of z, and then we have two different w's to choose, which is 2 here and minus 2. So then we have our 2 pi I, and then we have the quarter here from our partial fractions, so that's here. And then we have a 2, which is subbed in here, right? And then we have a minus 2, which is subbed in here. And of course, the minus here also carries over. So yep, pretty standard use of Cauchy integral formula. Now, we also have Cauchy's generalized integral formula, which is essentially if we have some derivative of f of w that we want. So if we have some holomorphic function f divided by a linear term, but that linear term is to a power, we can still use a formula like we did before, except it's a bit different. So we look at the power of the bottom term. So we take the powers n plus 1, and then we substitute this n value into these values right here. So we have this integral of f of z over some linear term to the power of n plus 1 for a simple closed contour to be equal to 2 pi I divided by n factorial. And then we have the nth derivative of f at w, which is where our singularity occurs. So something you might note is that if we substitute in n is equal to 0, this actually gets us our original Cauchy integral formula, which is why we call this the generalized Cauchy integral formula. So again, we will most likely be using the second form, which is why I have both here. So this is the one that you might see in your notes, but the second one is more common because generally we use it when we want to evaluate integrals. So here's an example of Cauchy generalized integral formula. And of course, you see that we have a circle of radius 4, and obviously that's simple and closed. And we have pi, which does live inside our circle, which is why we have to use Cauchy's generalized integral formula. And we also realize that z squared right here is holomorphic everywhere. So first we have our f of z, which we choose to be z squared. We choose our w to be pi and our n to be 2. The reason is because we have a power of 3 here, and we know that 3 is equal to n plus 1, so n is equal to 2. So now we just apply our Cauchy generalized integral formula, and we find that our answer is going to be 2 pi I divided by n factorial, but since n is 2, it's going to be 2 factorial, and the nth derivative, but since n is 2, it's the second derivative of f at pi. So we can just calculate what the second derivative is. The second derivative is going to be 2, since the first derivative of z squared is 2z, so the second derivative must be 2. And since it's constant, it doesn't matter where it is, so even at pi, it's still 2. So we can just sub in 2 into our equation right there, and we should get 2 pi I, because this 2 factorial and this 2 cancel out. So if we have an entire function f, and we know that f of z is less than z modulus to the power of k for some positive integer k, then we have to show that f is a polynomial of degree at most k. So the trickiest part about this is probably just figuring out what exactly we do from here, but if you see an inequality, it is actually quite a common trick to notice that this is a linear term to the power of k, and so if we divide both sides by this value, we should get a So first, we want to consider that we want a polynomial of degree at most k, right? So that means that our k plus nth derivative has to be 0 if n is a positive integer, which means k plus 1th derivative is 0, k plus 2th derivative, and so on. And so we can first transform our derivative through the Cauchy generalized integral formula to be in this form. And then, of course, generally, if we want to show something's equal to 0, you use something like the ML lemma. So first, let's address why we choose gamma to be a circle of radius capital R. So generally, we use a circle because first, circles are very easy to deal with, and secondly, we have the modulus being a value, like some constant, rather than having it be some variable. And so that would allow us to use the ML lemma, since it requires that we have a maximizer which is a constant. So first we can use the circle inequality. So we know that z minus w absolute value is greater than or equal to the absolute value of z minus the absolute value of w. So we can also have both sides be to the power of k plus n plus 1. And then we can also sub in our r, which we have defined our modulus of z to be. So what we've done is then we've taken the reciprocal of both sides, and we flip the sign, right? So now we can just first notice that the maximizer for this can be found by changing our modulus of f of z to our term right here. And oops, this should be just a strictly strictly less than. But then of course we can substitute in our second thing right here. So we substitute in this inequality and we should get that f of z over z minus w to the power of k plus 1 plus n modulus is going to be less than or equal to this right here. And since r is a real number and the modulus of w is a real number, since w is fixed for us, we can say that this right here is a real constant. So now what we have is we have the modulus of the derivative for k plus n is going to be less than or equal to n factorial over 2 pi times 2 pi r, which is the arc length because it's a circle of radius r, and we substituted in our maximizer that we found. And obviously we remove the I here because I has a modulus of 1, so if we take the modulus, it should be irrelevant. So now the reason we chose our circle is because obviously r is arbitrary. That means that this inequality holds for any possible r we choose. So we can, for example, have r approach infinity, and we know that r times r to the k would produce an r to the k plus 1, but obviously the bottom is a polynomial of degree k plus n plus 1. So if n is a positive integer, that means that the bottom has a higher degree than the top. So if r approaches infinity, that means that the limit would approach 0. So we get this inequality right here, and that basically shows that the k plus nth derivative is going to be equal to 0, since no complex number can fulfill this inequality. So we know that f is entire, which means we can represent it as a Taylor series, which we'll get into later. But that means that we have non-zero terms which are only up to the kth power. So that means k must be a polynomial of at most degree k. And of course the reason is because every derivative after the kth derivative is going to be 0, so no power after the kth power exists. So we have some minor theorems here. The first one is Louisville, which just says if f is bounded and entire, then f is a constant. So if you remember, bounded just means that every single value within f has a modulus which is less than some constant, and entire means that it's holomorphic on the whole complex plane. So we also have Moreira theorem, which basically just says if we have every single possible closed contour integrate to 0 for some continuous function f, then we can say that f is holomorphic. So you might notice that this is kind of the converse of the Cauchy-Gaussat theorem, because generally we have f being holomorphic, and from that we can imply that a closed contour would have an integral of 0. So this is just an example of Louisville theorem. And so we have to find all entire functions f such that f of z has a modulus which is less than or equal to the modulus of cos z. And so to use Louisville theorem, we can first find a function g, which is f of z divided by cos z, And the reason we do this is because we want G to be bounded, right? Because if G is bounded, then we can use Liouville theorem, and we can show that G is a constant. So, G isn't entire yet because we have places where cos of z is going to be equal to 0, and so the way we remove those is just by having g of z be equal to the limit as z approaches w for, this should be g of w be equal to the limit as z approaches w for g of z if cos w is going to be equal to 0. So that essentially just says that we patched up all of the holes which are caused by cos being on the bottom, and that makes our function g entire. So now what we can do is we have g of z being bounded, and so we use Liouville's theorem to say that g of z is some constant. And of course, we can multiply both sides by cos z, and we get f is equal to c times cos z, where c is some constant. But of course, the constant has some restrictions, because if we sub this f right here into our original equation, then we would be able to cancel the modulus of cos z, and what we get is c is less than or equal to 1, and so that is our final restriction, and we have the entire class of functions that f could be, which is c times cos z, where c is some constant that has a modulus of less than or equal to 1. So this is my part, and I'll be having Bruce take over now. So just a reminder to have all of your calculators be approved by UNSW. You can just come to Nucleus, and that should be all good. Just tell them that you want your calculator approved. They'll set you up, and they'll just give you the sticker. All right, thank you for coming. Just give me the sticker. All right, thank you for coming. And
Perfect. It looks like I can see myself. Just 1 second, I'll just test the sound. Just 1 second, I'll just test the sound. Alrighty, so you just heard myself. You just heard me speak to myself, but we're good to go now. Yeah, thanks Ronald for going through that. We're going to go through the last 2 sections of this course, which will be on series, and a nice little last section on Laplace and Fourier transforms. Alrighty, so we'll get started with power series. So this is basically the same as the concept we have in real analysis. We have a power series being expressed as a sum of powers of a given linear term. And it has the same kinds of rules as before, except everything can be complex. So the coefficients themselves can be complex, and we can also take z being complex, and the center itself of the power series, so z0, can also be complex. And we also have the idea of radius of convergence, except now it makes a bit more sense when we call it a radius, because we can see it on the complex plane. Right, so if you recall, the radius of convergence is the smallest distance is the distance. Let's just draw it out on a graph. We've got the center of convergence, z0, and then the radius of convergence tells us where the power series is defined. So if we've got a radius of convergence of r, it means that if you're within r units of the center of convergence, it will converge. And an interesting property we know about power series in the complex plane is that if a function is holomorphic, and we'll talk about this later, it is actually defined as a power series on that domain. So we have a few special rules. So if the series only converges at z0, meaning it's not defined outside, we say r is equal to 0. If it converges everywhere, so it's defined everywhere, then r is equal to infinity. And an interesting theorem that we'll use to calculate the exact values of power series is that a power series can be integrated and differentiated term by term, which means that if you want to differentiate this entire thing, you can just differentiate the individual terms and then sum them all up. And to obtain the radius of convergence of a power series, use the same concept as in Math 1131 and 1141, which means that you can just take the limit of the ratio of consecutive terms, an plus 1, take the absolute value of that, and then you'll get your radius of convergence. We'll do an example from the 2016 final exam, talking about these exact concepts. So first of all, the first part is quite theoretical. So the center is just going to be, we always express it as z minus z0, z minus z0 being the difference between z and z0. So you can actually express this as z minus, well, what would that minus be? It would just be minus 3. Right, so in this case, the center is just going to be equal to minus 3. What about the radius of convergence? Well, you can actually just use the theorem we just used, so limit as n approaches infinity of the ratio of consecutive terms. So in this case, it'll be n divided by n plus 1. Right, because we know that an is just equal to n, which means that an plus 1 is equal to n plus 1. And you can probably imagine what this ends up being, and just being 1. And the reason for that is just because it's a ratio of two linear terms. We just take the ratio of the coefficients. Alrighty, so the next thing is to find an expression for h. And to be honest, all of these questions are basically done in exactly the same way. And what I mean by that is you always reduce it to a geometric series, almost always. Right, in this case, we don't quite have a geometric series, right? So if you actually write this out, you'll get like 1 times z plus 3, plus 2 times z plus 3 squared, all the way up. That's not a geometric series, because with a geometric series, we don't have these coefficients. It's just a sum of powers. But what we often know is that when we have something like we've got an n in front of a power to the n, that's usually the result of differentiation, right? Because if you differentiate this term by term, which we know we can do, so just take a standard power series, so 1 plus z squared. If you differentiate this term by term, you'll get, well, this one just turned into 0. This turns into z. This is 2z. And it keeps on going up, right? Oh, double plus. But we've got a z cubed. It goes down to 3z z squared. So what we know from that is that when we differentiate a power series, oftentimes we'll get something like this. So it means that this is probably the result of differentiating something. So we can say that h of z, if we write this out, I'll just write this out. So h of z, the sum of n z plus 3 to the power of n. Well, it's really close to a differentiation, because differentiation, when you differentiate z minus z0 to the power of n, you actually get n times z minus z0 to the power of n minus 1, which is really close to this, because we've got n times this to the power of n. Well, the solution is pretty simple. We just take a z plus 3 out, so let's do that, and we've got this. And at this point, you can now write each individual term as a derivative of a simpler term, a simpler power term. So if you write that out, you get z plus 3 d on dz of z plus 3 to the power of n. I can't write, apparently. Cool. And so what we know then is that you can now take this out, because you can differentiate term by term. And then what happens is you've just got a geometric series here. Okay? And so as with any geometric series, you'll do this so many times over the course of the course. But just write out what it looks like. This is equal to the sum from n equals 1 all the way up to infinity of z plus 3 to the n. So it starts with z plus 3, goes all the way up. And what you'll find is that you've got this sum of linear terms. And with any geometric series, you just start with, if you remember from even maybe 2-unit maths in high school, the geometric series a plus ar all the way down is equal to a divided by 1 minus r. So same kind of thing over here, you just take the first term, z plus 3, then you do 1 minus, in brackets, z plus 3, which is equal to z plus 3 on minus z minus 2. Yeah. Seems there might have been a bit of an issue here, but we'll just continue down like this. Let's just say we've got this geometric series. What you do is you just turn this into a geometric series. So you've got that a divided by 1 minus r term. And what ends up happening is you've got the derivative of that you just express in terms of a fraction. And that ends up being, because you can just differentiate powers like minus 1 on z plus 2. You just differentiate that to get z plus 2 squared using the power rule. And you end up getting this. Okay, so it's really just a matter of differentiating the term that you get overall, and you'll end up getting a simple function in terms of z, and that answers part B. Part C is pretty similar to the rest of it, whereas H analytic. So that's just asking where it's differentiable. And so what we know about this is that it's going to be differentiable on that ball, and the ball is going to be the ball around the center. Because we know that when we have a radius of convergence around a point like minus 3, and the radius of convergence in this case is 1, all that means is that the ball around minus 3 with a radius of 1 is defined there. And so we can actually just write as equal to b minus 3, 1. Cool. And that's our answer to part C. Okay. This is another type of question, but they're all really common types of questions, so it's very useful to go through. In this case, we've got a very similar example where we want to find exactly the same kind of stuff, like center, radius of convergence, and then the expression for f. But the only difference is now instead of having an n outside, we've got a 1 divided by n plus 1. Before we do that, though, let's just reduce it to the standard form. So recall that we've wanted something like that looks like this. We wanted something looking like this, and so this is really different because now we've got a 2 in front of it. And so all we have to do really is just take the 2 outside. And what you want to do by doing that is just take the 2, and because we've got to the power of n, we need a 2 to the power of n. And so now we're basically in the right form that we want. We've got 2 to the power of n divided by n plus 1. All of that multiplied by the power term. And then we can proceed. This is just our an, right? That's really what we want. And so with center, it's really just a matter, sorry, I forgot to divide by 2. But if you divide everything by 2, you get a z minus 5 on 2. And so then you discover that the center is going to be 5 on 2. So it's really important you get it in the right form. Like you might be tempted to say right now, oh, this is just 5. The center is 5. But really what you need to do is just take out the 2, and then hopefully you also remember to divide by 2 unlike me, and then you'll get a z minus 5 on 2, which means your center is 5 on 2. As for radius, again, look at this is an, and then you just use your formula for radius of convergence using this thing over here. So I'll just take this over here. You just take the ratio of consecutive terms. Linear terms just cancel out, who cares about those? But all we really care about is the power terms. We've got 2 to the n divided by 2 to the n plus 1, which is just equal to a half. So the radius is a half. The next part is actually looking at how to actually calculate this power series. And before we expressed each term as a derivative of a simple power term, but in this case it's actually the opposite, right? It's actually we've divided by n plus 1. And so what you actually want to end up doing is instead of saying this is equal to d on dx of something else, you instead differentiate this and aim to try to cancel out the n plus 1. So let's do that. Let's just write this out. So yeah, it says we notice here n plus 1 in the denominator. We generally want to take the derivative of the power series to reduce it. And so let's just write out what we had. So it's this thing. Sorry, I just saw someone's comment. Okay, 1 divided by n plus 1. Yeah. Okay, so yeah, we had this over here. And we basically wanted to remove the n plus 1 term. And we know that when we differentiate, let's say we differentiate this thing, we've got n times z minus 512 to the power of n minus 1. And so what happens is the power comes down, and you multiply through by the power. So in this case, if I just differentiate fx directly, so I'll just say d on dx fx, if I just differentiate that, I won't actually cancel out the n plus 1. So it's not quite right, because when you differentiate it, we're basically aiming to cancel out this n plus 1 so that we just get a power series. And so what we probably want to do instead is actually multiply through first of all, right? Because if we multiply fz through by 2z minus, or let's just do z minus 512. If I multiply through by that, then I actually get an n plus 1 at the top. And so what happens is that when you differentiate it, this actually comes down, and you cancel that out. And so let's look at how that works. Essentially, we've just done that over here. We've got d on dx of z minus 5 on 2 times fz. And all of that, if you get that, it all cancels out. You get the derivative of this. Then this thing comes down. So you've got a 2 to the n. And then this changes to n. So n plus 1 changes to n. So you've differentiated this term, and you've cancelled out that annoying little n plus 1 over there. And so this actually turns into a geometric series. And you can actually rewrite it to make it a simpler geometric series. 2z minus 5 to the power of n. And so what ends up happening is you've got this geometric series that you just write it out. And then you can actually use what I just talked about, which is just the same thing where you do a divided by 1 minus r. So you've got 2z minus 5. There'll be 1 minus 2z minus 5 on the bottom. And you'll end up with this. And so really, now that we've got like this formula involving derivatives and our original function f, what you can do is you can then try to reverse it to get to f. So what would the antiderivative, for example, of this thing be? You get z minus 5 on 2 times fz is equal to minus z. And recall that when you integrate a reciprocal function, you end up getting a log. And so you end up getting this. There's actually a bit of a caveat that makes this more complicated, because recall that log isn't actually continuous everywhere, right? So if I actually draw this out, where is this equal to 0? Where is this equal to, let's take this over here. If you try to imagine where the singularity would be over here, the singularity occurs at 0, right? So where 6 minus 2x is equal, 2z is equal to 0, you'll get a singularity. Which means that we get a singularity at this point over here. And so if you actually just write this all out, then what you want to do is just try to solve for the constant. Because when we integrate, we do get a constant of integration. And so in this case, what we want to sub in is the most obvious one to sub in, the one that makes both sides equal to 0. So in this case, you could probably sub in z equals 512 on the left-hand side. And then what will happen is you'll get this is equal to 0. This is also equal to 0 because you get 6 minus 2 times 5 on 2, which is equal to 1, and that's equal to all 1. So what happens is you get 5 on 2 minus 5 on 2 times f5 on 2 is equal to minus 5 on 2, minus half log 0, 1 plus c. And so that all cancels out, you get c equals 5 on 2. And so when you get that, you end up getting fz times z minus 5 on 2 is equal to this. Then you can divide through by that, and you end up getting fx is equal to this. And the reason why we have this piecewise function is just because we know that we can't always divide by z minus 5 on 2, right? We can't divide by that when it's equal to 0. So in the case where x is equal to 5 on 2, what ends up happening is we have to think about the limit as we approach that line. And so looking at this thing, looking at our original function, if I just erase all this, what would this actually look like if we had x is equal to, oh sorry, not this question, this one. What does this thing actually look like at 5 on 2? Well, if you actually calculate it all out, we always have 2z minus 5 in the term, which means we always have 0. So this function is actually equal to 0 when z is equal to 5 on 2. And so what ends up happening is that at this point, we can just use the original value of our function to calculate that it's equal to 0. All right, and so that's why we have a piecewise function, because we had this condition where we're dividing by 0, and that means we have to chuck in an extra case there. Okay, so we'll move on to Taylor series. So what a Taylor series is a holomorphic function. And so the interesting thing about complex functions is that every single holomorphic function can be defined as a Taylor series, right? It's not like real analysis where you have certain conditions on that. If you have a holomorphic function on a board, you can define a Taylor series on it. And so a Taylor series around 0 is also called a Maclaurin series. And that means we can also use the common Maclaurin series that we remember from first year, which is like, for example, e to the x is equal to 1 plus x squared. To change this to z, all you really have to do is change it to a complex number. E to the z is equal to 1 plus z squared. And that's a common Maclaurin series. And something like sin x, which you've seen before, is exactly the same as what you've seen in real analysis. So a simple example of how to apply that is you've got fz is equal to z plus 2 times e to the 3z. And if you want to write that out, all you really have to do is just sub this into our common Maclaurin series. But generally when we want to do these questions, we want to do it using sigma notation. And the reason for that is just because we want to be able to simplify everything in terms of one original term. So what you'll do is f of z is equal to z plus 2 times the sum from 0 all the way up to infinity of, it should be 3z to the power of I. And the tip to then expanding that is just to write this all out. Oops. You've got 3 to the I times z to the I. And then you can actually expand each of these terms individually out, and you'll get some z to the I plus 1 times this. And so what ends up happening is you've got two different terms, and we'll see that you can sum them together by just changing the variables. So what we've got over here is we've got a sum of two different things. So z to the k plus 1 and then z to the k. And what you do is you just actually change this. This is actually the sum from k equals 0, which means you go from the term z. So the first term over here in this sum is 3 to the 0 times z to the 1 divided by 1 factorial. And so what you can do is you can actually, instead of having a sum from k equals 0 to infinity, you can change this to a sum from k equals 1, where instead of having z to the k plus 1, you have z to the k, and you decrease each of these by 1 as well. So 3 to the k minus 1 divided by k minus 1 factorial. And so that's what we've done on the next line. Then the final thing that we do is we just combine these two things. We combine the two terms from the different sums by taking out the z to the k. And then that's our final formula for the Taylor series of the exponential function. Cool. Now looking at a different kind of series, because sometimes a function won't be holomorphic at a point, but you can still represent it using power series. But what happens is, let's just say, for example, we've got a bunch of, we've got a function, and it's not defined at certain points. So I'll just say these red points are points that it's not defined on. And what we'll say is that we want to find the representation of maybe this point, f at this point, around the center, let's just say over here. This is not, we're not going to be able to find a ball that's holomorphic, on. So does that mean we can't actually construct a power series? It doesn't, because what we can do is we can instead try to avoid the singularities. So what you can do is you can take an annulus. An annulus is like a donut. What you're doing is you're taking one ball and you're excluding the points within a ball in the center. So I'll just draw it out. So like, for example, this is an annulus. We're taking one ball and we're removing the ball on the inside. And so what we can do is, let's just say we want to represent this point as a power series around this point over here, Z1. Well, you can just take the entire ball, but then subtract all of these points. And so if this first radius is like R, the second radius is like, is lowercase r, then you're taking the annulus over here. And you can still define it as a power series, but you'll need a different concept called Lorentz series. Cool. And so let A be the annulus, B, Z0, R2, R2. R2 is the outer radius. And then you subtract the stuff on the inner radius, so R1. And what you'll do is that if F is holomorphic on that annulus, so it doesn't need to be holomorphic everywhere, just on the annulus, then we can actually express it as a series, but this time we have to include negative powers as well. So before we had n equals 0 up to infinity, now we have from n equals minus infinity to infinity. So an example would be like if we had f of z is equal to 1 on z plus 1 plus 2z, all the way up to infinity, then what you'll get is that's a Lorentz series because it includes negative terms. So a classic example is finding the Lorentz series over here, in the annulus over here, which means we have a center of 1. And so this is we usually don't like to have like multiple terms on the denominator. So what you want to do is try to separate this out into partial fractions. And so we've gone through partial fractions before. I'll just provide you with the actual answer, the actual expansion. But what you'll notice over here is we've got something with z on the bottom, something with z minus 1 on the bottom, and something with z minus 2 on the bottom. This one is easy, z minus 1, because it's already in the required form. We want a Lorentz series around z minus 1, which means we have a bunch of terms with power z minus 1. And then we also go negative. And so this is just an allowed term. We can actually just have this as a term itself. But these terms over here with the z and the z minus 2, we can't have by themselves. Instead, we need to use what I said before, which is the geometric series. So I'll just explain it with 1 on z. So 1 on z is not what we want. We want something with z minus 1. So what we can replace it is z minus 1, and then we add 1 back. And so the reason why we do that is because remember the formula for a geometric series. If you have 1 on 1 minus r, for example, then that ends up being 1 plus r squared all the way down. And so if you do the same thing over here, if you do z minus 1 and you also have a 1, then what you can do is you can express it in the form 1 minus, and there will be 1 minus z. Right? So 1 minus this term. And so the benefit of that is if you use this expansion, you get 1 plus 1 minus z all the way down. And you end up getting something with the required terms, right? Because we wanted stuff with z minus 1 in our Lorentz series. And so that's a really nice way we can do this over here. But there's one thing we have to be wary of, which is that we need to make sure that this actually converges. Because this thing over here, 1 minus z, might have a, the restriction on this is that the absolute value needs to be less than 1. So we need to make sure that 1 minus z is less than 1, or its modulus is less than 1. In this case, it actually isn't, right? So we've actually been told we want the annulus where it's greater than 1. So we actually have to do something else over here. and I'll just draw that out over here. So what do we do instead? There are always two options of what we can do in this kind of scenario, where we have like two terms on the bottom. Either we can make this one effectively become the 1, and what I mean by that is that in any geometric series you have 1 minus r. One of these terms is going to be transformed to be the 1, the other term will be transformed to be the r. And so either of these terms can be the 1. And we tried making this one the 1, and what ended up happening was that the other term, the r, was actually not in the required region. Its modulus was greater than 1. So in that case, when we do that, we do the other option. And it's always guaranteed that that will work. So we do 1 plus, we actually divide the numerator and denominator by something in order to make this 1. In this case, what do you divide z minus 1 by to make it equal to 1? That would be z minus 1. And you end up getting this. Right, so what we've got here is we've got a very similar situation. We've got 1 minus something else. But in this case, this actually follows the required form. Its modulus is less than 1. And so what you do here is you do 1 on z minus 1, then you just expand the geometric series. So 1, in this case, it should be minus. Oh, sorry, that's not meant to be squared. Yep. So, yeah, so what you end up getting is that all of these end up being powers of z minus 1. And in this case, it actually converges because we've done the option where this has a modulus less than 1. Okay, let's do the other one as a practice as well. Let's add a page. Oh, no, it's just this button. Yeah, let's add a page. So let's do the other one as a practice. So 1 on z minus 2. Is equal to 1 on z minus 1 minus 1. And similarly, we could just change this to be equal to minus 1 on 1 minus z minus 1. But we already know that that's not going to work. So instead what we have to do is we have to recall our transformation. We have to make this term, z minus 1, the 1 of our term. So instead we divide by z minus 1. Oh, sorry, that should be 1. And instead it ends up being that. So then we get 1 on z minus 1 times 1 plus 1 on z minus 1 squared plus 1 on z minus... Sorry, I keep on squaring things when I shouldn't. And it goes all the way up to infinity. And so what you end up getting is you get a very similar sum of terms in the form z minus 1 to the power of k. Let's just see how they've written it out. It's actually exactly the same as what we just did, except they formalized it by instead grouping the terms together. So you've got a bunch of terms with z minus 1 to the power of n, z minus 1 to the power of n over here. And so what you do is you just consider the coefficient of each term, and if you just do that manually, you'll figure out that it's equal to 1 in the cases where n is equal to minus 3, minus 5, and so on, but 0 in all other cases. And that's that example done. Alright, so this question is very similar, but we have to think a bit more about, when we're talking about like z plus 2, for example, and we want to transform this to be 1 minus r, and we said we have to choose one of these terms to be the 1, the other one to be the r. Well, this question is just forcing us to think a bit more about which of these to choose to be the 1. So something like this, again, it's going to be in powers of z minus 2, so we know we have to change this bottom term to z minus 2 plus 2 plus 2i. And so which of these terms are we going to choose to be the 1? Well, which of these has a bigger modulus? Because we want the Lorentz series that converges when z equals I. And so that means it's best to actually draw this out. So we've got 2 over here, we've got I over here, we've also got minus 2i over there. and we've got 4 over here. Okay, and so let's just break down what each of these points is. This is the center. This point is the point that we're trying to find the Lorentz series of, and these 2 points are singularities that we want to avoid. Remember when we said we want to draw annuluses so as to avoid our singularities? Well, these are the things we want to avoid. And what we do is, because we're finding an annulus, we find the distance of each of these points from 2. So this point has distance 2 units, this one is distance 2 root 2 units, this one is root 5 units. And so we try to order them because we want to find, we basically want to sandwich this in between 2 other singularities. So if we've got a root 5 here, then that's actually between the other 2, right? So this is between the other 2. Root 5 is less than 2 root 2, is greater than 2. And so that means that what we want to do is we want to take the annulus outside this one, so outside the one with units with radius 2, but below, within the one with radius 2 root 2. And then if we take that, because this bigger one, if you recall from our notation, capital R is equal to 2 root 2, lowercase r is equal to 2, then this will lie within that annulus. And so to summarize what I've just done is we've taken the annulus, if we write this on the next one, so we want to find the Lorentz series in the annulus is between 2 and root 8, or 2 root 2. Okay, and so that gives us a bit more clarity in terms of which one, in terms of breaking these terms down. Alright, so let's just do that as well. So let's look at this. So again, we said before it's 2 minus z minus 2 plus 2 plus 2i. And so the question we were asking is which of these has the bigger modulus? Because this one has modulus, it's going to be between 2 and root 8. And this one is going to have modulus root 8. And so which of these has the bigger modulus? Well, it's going to be this one, which means that this one is going to turn into the 1. Because when we divide through 1 plus z minus 2 on 2 plus 2i, when we divide through, we're actually dividing, we're turning this one into 1, but then we're dividing this one by the other one. So we've got z minus 2 divided by 2 plus 2i. And so because this one has a bigger modulus, then the modulus of this thing will end up being less than 1. Yeah, and so we can just write that out. We've got, I'll repeat, 2 on 2 plus 2i, divided by 1 minus, and then you can do a 2 minus z on 2 plus 2i. Alright, well we just took this, and we took the minus of that. Z minus 2 times minus 1 is equal to 2 minus z, and so we've gotten this term over here. And so we can imagine you can also write this all out, you can expand this all out, and you'll get something. And so let's just look at this one. It's all very much the same process. So in this one we've chosen to make this one z minus 2 divided by 2 plus 2i. Then we turn this term into this geometric series. Same thing over here. We take this one and we say turn this one into that geometric series. Right? And the whole point of it is just that everything needs to be in terms of z minus 2. Which means that when we write this all out, you get a nice Lorentz series in powers of z minus 2. And what they often do is you take the individual terms and you find the CKs. So if you recall, CK was a notation for the coefficient of z to the k, which basically means that we just group all the terms together, all the like terms together, and then find the values of the coefficients. We'll move on to singularities now. So singularities, unless there are any questions, if there are any questions, just mention in the chat. But singularities are just an extension of what we talked about. So an isolated singularity is a singular point for which it's not differentiable at that point. So the function f is not differentiable at that point. But what we know is that it's actually holomorphic everywhere else. So there is a ball, you can draw a ball around it, it's actually holomorphic around it, it's just something went wrong at that point exactly. And there are several types of singularities, which we can all actually explain using Lorentz coefficients. So suppose that f has an isolated singularity at z0, and it has Laurent coefficients Cn. And so assume f is not equal to the zero function, because that's a bit boring. And so there are actually three possibilities, and you can actually intuitively understand them all in terms of the Laurent series. So the first one is that there are no integers n is less than 0, where Cn is not equal to 0. So what that means is that there's actually no like negative power terms. So recall we had like a function like, this is the Laurent series, like z to the minus 2. What we're saying is that there are no integers less than 0 that actually have a non-zero term. So these terms don't even exist. And so the question is, why is there even a singularity? Well, it's called a removable singularity, because you can very easily just remove it by defining the function at that point. So if you recall from like real analysis, we also had this concept. If you've got a function, it's like fine everywhere, except one point it just screws up, like it goes over there. Well, that's actually pretty easy to remove. You just define a new function where the new value of the function at this point is equal to this. And so that's the same concept in complex analysis. If when you do the Laurent series, you don't get any negative terms, then that means that you can actually just very easily define the function at that new point. And then you'll remove the singularity. The second option is that there's some non-zero finite number of integers, less than 0, that have a term in this Laurent series. Which means, for example, if I just write this out. If I just write this out, then we've basically got we've got what's called a pole, right? And so you'll see that the highest order like negative term is z to the minus 2, and we can actually use that to define what's called the order of the pole. The order of the pole is the sign, is the magnitude of this highest power. So this is a pole of order 2. Yeah, so that's a pole. And the last option is if there's no pole, there's no like highest order negative term, it actually goes on forever. So we've got fz equals, and it never stops, right? There's a z minus 2, there's a z minus 3, and it keeps on going until minus infinity. In that case, we call it an essential singularity, because you can't remove it at all. You can't do anything with it. It just keeps on going off into the abyss. Okay, so there's another way we can test for which type of singularity we have. So this is kind of like formalizing what we said before. If the limit of the function itself exists, then it's removable, right? Because what that means is that as you approach the point, you get a limit, which means it's actually defined, which means it's very easy to remove, which means you don't actually have that annoying z to the minus 2 term. That's the first one. This second one you can also understand by using the Laurent series. So if you've got like the Laurent series, let's say you've got a pole of order n, it goes all the way up to minus n, so it would go to like z to the minus n, all the way up. If you calculate the limit, if you multiply through this function by z to the power of n, then you're basically removing all of that. You're turning this to a normal term. Turning this to a 1, this will be a z, and all the way up. Which means that now this function is actually holomorphic. So if this limit exists, then you can use that to see that it's a pole. And the way to test the order itself is to see the first number such that it actually exists. Because for example, if I take this function, and just multiply it by z, I just multiply it by z, then it's still not going to be defined, right? The limit won't be defined because we've not gotten to, we still have reciprocal terms. But the idea is if you keep on doing this until n, the first one that it's defined for is going to be the order of the pole. right? So you can use this test as well to test what order the pole is. So if z to minus z to the z0 to the power of k exists for k equals n, but not for any of the ones before that, then you've found the order of the pole, that's order n. Lastly, if you keep on doing it and you keep on trying to multiply it through by power terms, but it never actually exists as a limit, then you've got what's called an essential singularity. Yeah. This is just a formal definition of what we just talked about. So suppose it has a pole, then there exists a number m such that the coefficient is not equal to 0, but also for all n is less than m, it is equal to 0, which is just what we talked about, right? So the coefficient is not equal to 0 over here, but then everything else doesn't exist. So z to the minus 3, there's no term. Z to the minus 4, there's no term. In that case, we say that the pole has order, and they say minus m because what they've done is they've said that m is the negative number, so m is, like in this example, minus 2. But you can just take the absolute value. The pole has order 2 in this case. And what we call a simple pole is just a pole of order 1, which means if you can imagine it, it's something that looks like this. The lowest term is z to the minus 1. This is another concept that we've seen before in real analysis, so zeros. So suppose that we have a function, right? And if you look at the coefficients of the Laurent series, there also exists an m is greater than 0, such that the coefficient is not equal to 0, but then also all terms before that are equal to 0. So in other words, it's just the first term as well, except it's called a 0 because we don't have reciprocal terms. In this case, it'll be a 0 of order 2. So each of these definitions is just looking at the lowest order term. Alrighty, so this question is looking at poles and zeros. So classify the singularities. So what you want to look at is where the function is not defined. In this case, it's where z squared plus pi squared is equal to 0. And if you expand that, if you factorize that, it'll be z plus pi I. Z minus pi I is equal to 0. So in other words, there are two singularities, minus pi I and pi I. And so the way we check, singularities, the way we check the nature of the pole is just by multiplying through. So what you can actually work out is that if you multiply through by just a single linear term, the term on the bottom cancels because this is equal to z e to z plus I pi, z minus I pi. If you multiply through by, for example, we're checking at I pi, if you multiply through by that, you end up getting something that's perfectly well defined because there's only z e to the z, which is always defined, and this thing which is always defined except for at minus I pi. And so because once you multiply it through by z to z minus I pi, you get a limit. So typically you just sub it into this, so you get I pi, sub this into that function, you get minus a half. That means you get a simple pole at this point. Because all it took was just to multiply it through by once. And you can probably sense that this was going to be the case because the numerator is just a normal function. And then on the bottom, you just have one linear term. You do the other one, same kind of idea. You multiply through by z plus I pi. And then you end up with z minus I pi on the bottom. And you can just get that to be minus a half. And that's another simple pole. Alrighty, so we'll talk now about residues. So the residue of a function is defined as being equal to c minus 1. And if you recall from our notation, but before we talk about that, I should clarify something. So there are two things you need to define a residue. One is the function itself, the other is the point, right? Because what you need is the function, and you also need the point about which to do the power series. So f of z is equal to some constant c0, and then you start doing the power series about z0. Right, and so what you do is you do that power series, then you calculate the coefficient of the reciprocal term. So c minus 1 is just the coefficient of z minus z0 to the power of minus 1. And so that ends up being the residue. And so one way you can calculate the residue is there's a formula for the residue. The way you can think about this is that when we've got this function fz and it's got a polar of order n, we want to first multiply through by z minus z0 to the power of n to make it continuous and holomorphic, but then we differentiate to try to make the n to make the n minus 1 term, because when you multiply through by z to the n, this term that we want, right, because we're trying to get the coefficient of c minus 1, when we multiply through by that, we end up getting this becomes n minus 1. So what you want to do is to make this a constant term, you differentiate n minus 1 times. But you don't have to go into the dynamics of that. This is just a formula you can remember. Basically, all you're doing is multiplying through by z to the power of n, then you're differentiating n minus 1 times. Okay, so this is an example where you can calculate residues. And so some of them, looking at the singularities, well, first of all, how would you calculate the singularities? We have singularities where sine squared z is equal to 0, and that's where sine z is equal to 0. And that's where, if you recall, z is equal to k pi for k an integer. So if we look at this term by itself, then we're thinking about the numerator as well. So sometimes the numerator will also be 0, right? Because if the numerator is also 0 and the denominator is 0, then sometimes it'll be removable, right? Because they'll cancel out. And in fact, if you look at this by itself intuitively, and you look at the terms that make this 0, so the numerator is 0, where z equals 0, or where z equals pi. Let's just look at z equals pi first. So z equals pi, let's just ignore this because z is just a normal function. We're taking out this. And what you'll notice is that this is actually a normal linear function, and then it's divided by sine. And what you might recall from your complex analysis is that these terms will approach, the ratio of these terms will always approach 1. And so the limit actually does exist if you calculate the limit. So the limit as you approach pi does exist because this is just a linear term and this is just a sine term. And because their powers are the same, we've got a square divided by a square, they should cancel out to be 1. And so the limit of this is actually just equal to the limit as z approaches pi of z times z minus pi sine z squared. And this becomes just 1. So this ends up being just pi. And so because it's a removable singularity, don't think the answer is pi, because that's a different limit. Recall that the residue is going to be the coefficient of the reciprocal term. So if it's removable, there's no reciprocal term, right? If there's no reciprocal term, then the residue will be equal to 0. The second one is going to be equal to a simple pole, because we've looked at z equals 0. That's the other one that makes the numerator 0. We've only got one z term on the top, but then we've got two sine terms on the bottom. So that's the effect, that has the net effect of having a one linear term on the bottom, which is why it's a simple pole, right? In fact, if you want to check that it's a simple pole, you take the residue. And recall the formula for the residue. So if you've got a pole of order n, let's just try to remember it for ourselves. Pole of order n. You want to multiply through by z0 to the power of n, then differentiate n minus 1 times. In this case, we've got a pole of order 1, so we multiply through by the linear term, but then we don't differentiate at all. So you always differentiate one fewer times than you multiply by. And so in this case, we've multiplied by z, but we don't need to differentiate at all. And so once you've gotten that, you'll get z on sine z, which, as we talked about just then, just becomes 1. And then you've got z minus pi squared, and that ends up being, when you evaluate it at 0, just pi squared. Cool. The next one is looking at all other cases where you've got k pi. In this case, it's actually a polar of order 2. And we hopefully should be able to see that too using our intuition, because these functions don't vanish. They're actually just normal functions that don't vanish at those points. So it's effectively equivalent to a constant, right? Whenever you have a function that doesn't vanish, you can just treat it as a constant, right? So what you've got over here is, instead you've got two things on the bottom. So what that means is that when you use the residue formula, you multiply through twice and you differentiate once. If you actually try to do this, you'll get something really annoying, and we don't want to be annoyed. So more likely, we'll actually just try to find the coefficient of z minus k pi to the minus 1. Okay, so what we want to do in order to do that is express everything in terms of z minus k pi. So express the top in terms of z minus k pi. Express the bottom in terms of z minus k pi. We'll start with the bottom, because that's going to be a bit more complicated, having it on the bottom. And if you do this, you'll actually get this. Because we know the Taylor series per sine above z minus k, about z equals k pi, and you'll get this thing squared. And so what you'll notice is that when you actually divide by that, because we've got it on the bottom, you'll have 1 divided by this entire sum squared. Yep. So it'll be this entire sum squared. But the issue is that when we have something on the bottom, we can't actually, it's not in the right form, because we want like just normal terms, like 1 plus z multiplied by the actual term itself. And so what you'll notice is that instead of actually having that, we need to expand out this sum itself. And the reason for that is because we want the denominator to be equal to 1 minus something. Because whenever we have a fraction with something on the bottom, we generally want to turn the bottom into that geometric series from before. Like we want something like 1 divided by 1 minus z, so that we can expand out all the z's. That's what we've done over here. So if you expand all of this out, you'll get this. And so what you want to do is you want to you look at this expansion, you do the sign expansion, and you generally want to take this thing out, so the z minus k pi. And so the reason for that is to turn this into a 1, because we were talking about when you have a denominator, you want to change everything to be 1 minus something. So you take out the z minus k pi squared, and you end up with this. And that ends up looking pretty good as well, because then we can just express this as equal to 1 divided by z minus k pi squared. All of that equal to the geometric sum of all of these things. So z minus k pi squared on 3 factorial all the way down. And that doesn't look super good, but the reason why it's okay is because we're only really looking for the coefficient of the minus 1 term. So it's okay that this looks really confusing and massive, because we're only after one term. We're not after the entire expansion. So now all we have to do is just rewrite the entire term in powers of z minus k pi. Right? And so if you actually do all the maths, you'll end up getting something like this. We want to turn the top into terms in terms of z minus k pi. So what you do is you turn z, the classic trick of turning z into z minus k pi, all the way plus k pi. Same thing over here with z minus pi. You want to do z minus k pi, and then plus k pi minus pi. And so that's what we've done over here. We've changed everything to be in terms of z minus k pi. So putting this all together, we've changed everything in our term to be in terms of z minus k pi. And so now the only thing to do is to find out the coefficient of minus 1. And so let's just, it looks really intimidating, but let's just break it down. We've got z minus k pi there, z minus k pi there, and then we've got 2 z minus k pi's here. Then over here, we've got like, if you think about what this term is, it's 1 plus all of this to the power of 1. So z minus k pi squared So all of this to the power of 1. Then you do all of this to the power of 2. Right, so that's this term. And then we've got these terms over here. So think about what we're after. We're after something where the final coefficient is -1. So we've already got a -2 on the bottom. So we need to multiply all of these terms. So I'll just take this as term 1, this is term 2. And this thing over here is term 3. We want to combine terms 1, 2, and 3 together. We want to take terms from 1, 2, and 3 and multiply them together in order to get a total power of 1, right? Because we've already got a 2 on the bottom, and then these consecutive terms need to multiply through in order to get a power of 1. So in other words, it's like we're picking terms from each of these individual brackets to get us to a total power of 1. If that's confusing, maybe think about like a simpler example. This is very behind, apparently. Where am I? Okay. 1 second. Okay, I don't know why R is open. Am I back? Oh, okay, I am back. Okay. That's cool. Very cool. Let's go back to doing stuff. Okay, I'm not sure where it stopped working, but I believe I am live now. So I'll just go back to explaining this. We've put everything together. And now I was explaining the concept of when you're multiplying different brackets together, and you're combining different brackets together to get the final coefficient of a single term, for example, z minus k pi to the power of -1, which is what we were doing, then what you want to do is you want to search through the different terms and then find terms individually that multiply through to create the power you want. So I use the example of 1 plus z times 1 plus z times 1 plus z. So if you want to find the final coefficient of, for example, z, what you want to do is you want to multiply through, find all the different options of terms from the different brackets that you can multiply through by in order to create something with power 1, right? So in this example, you can do 1 times z, which is where you pick the 1 over here, you pick the 1 over here, you pick the z over here, or you can pick the z from the middle one, or you can pick the z from the end one. Right, and the reason and what ends up happening is you get 3z, which is why the coefficient of z is equal to 3. So same kind of thing, we're trying to find the coefficient of z minus k pi to the -1. So what you want to do is go to each of these factors. So this is factor 1, this is factor 2, this is factor 3. Because we've got these 3 factors, we want to combine the individual terms to make the total power. In this case, it'll be equal to 1, right? Because we've got a z minus k pi squared on the bottom. So if we want to find the coefficient of z minus k pi to the -1, all of these terms at the top need to multiply to create something with power 1. Okay, so in other words, we're going through 1, 2, and 3 in order to find terms that multiply through to create 1. And that makes life really easy, because if we look at term 3, it's got 1, right? It's a geometric series. We start with 1. Then we've got this massive annoying term, z minus k pi squared divided by 3 factorial minus z minus k pi squared to the power of 4 factorial. All the way up. All of that to the power of 1. Then we've got all of that to the power of 2. And the whole idea is that, if you actually think about it, every single term here, other than 1, has a power greater than or equal to 2. Which means that when we go to multiply things together, it's not going to be possible for us to use any term in this bracket expansion other than 1. Right? So this entire expansion, we can only use the 1 in the expansion. Right? So let's just write that out. To find the coefficient of 1 on z to the minus 1 on z minus k pi, we'll use the 1 from over here. That means from terms 1 and 3 together, the terms we multiply together need to have term 1, right? Need to have power 1. So what we can do is we can potentially, let's just write this out. This is a square, but we should probably write it out completely. This is actually exactly the same as what I just showed you with the 1 plus z, 1 plus z, 1 plus z. Because if you want a total power of 1, you can only take z minus k pi out of one of these brackets. The other two, you have to take the constants. So in other words, this expansion will be equal to, I'll just write this on a new page. If you just expand the terms that we want, we'll get z minus k pi. All of that times pi k minus 1 squared. That's the one I've picked over here. Where you pick the first z minus k pi, then you take the constants in the other one. Then you take the next one, which is z minus k pi, times it by k pi over here, and then pi times k minus 1 over there. And then you take the last one, which is z minus k pi. You select the z minus k pi over here. Then you do the same thing over here. And so you'll end up finding out that the coefficient is equal to this sum. So that's what we've got on the next page. We've got this thing. You expand it out nicely, you just get a pi squared on the outside, but that's our required coefficient. Okay, perfect. We'll move on to the final section before we move on to Laplace and Fourier transforms, which is Cauchy's residue theorem. So this actually generalizes what Ronald was talking about earlier with Cauchy's integral theorem, because what you can do is given any domain where you've got a number of singularities, so singularities are z1, z2, all the way down to zk, you can actually calculate the integral around all of these singularities, right? So if you've got your singularities inside, you can calculate the integral of the contour around these singularities by just calculating the sum of the residues at those singularities and multiplying by 2 pi I, right? So just calculate the sum of these residues, then multiply through by 2 pi I. Okay, and so this is actually going to ensure that we can essentially calculate any contour integral, even if there are singularities on the inside. So let's move on to a question that brings all this together and talks about residues in general. So consider this function. Fz is equal to this thing. And as with any question where we're asked to find singularities, we just want to find the sections where the denominator is equal to 0. So let's just expand this out. We've got 2z to the 4 minus 5z squared plus 2. Well, we can expand that out because this is a quadratic in z squared. And you'll end up getting that it's equal to 2z to the 4 minus 4z squared minus z squared plus 2. Equal to z squared minus 2. 2z squared minus 1. And you can see what the singularity is going to be. They're just going to be the real numbers that are the roots of these polynomials. So simple poles over here, at plus or minus 2, plus or minus 1 and root 2. And the reason why we know they're simple poles is using that intuitive explanation, where this is a function that does not vanish, like z does not vanish at these points, divided by this product of linear functions, where all of the linear functions are different, which means that at any given point over here, there's only one linear function on the bottom. So they're all just going to be simple poles. The next part is calculating residues. And residues, it's pretty easy to do just using the limit. All you need to do is just take the function, multiply it through by z minus minus that singularity, and then take the limit, and it'll be equal to a 6. So it's just going to be more algebra that we've done a lot of, but the residues will be equal to a 6 each. And so the final question is actually not directly asking us to calculate the integral, but you can kind of sense when they give us a real integral that what you want to do is first calculate the complex integral and then somehow link this to the real integral. So let's think about what this integral looks like. It's from 0 to 2 pi, which generally means that we're doing a circle, right? Because we've got a cos in there, somehow this is going to reduce to a circle. So what we most likely want to do is look at this function and then try to evaluate it around a circle. And if we do it around the unit circle, they've told us, if we do the integral around the unit circle, then what we can do is somehow take that integral, so it'll be fz dz, do the parameterization in terms of theta, where we go from 0 to 2 pi, and then somehow this integral will transform into this one. So let's do this over here. So we're doing the integral around the unit circle, and it's just going to be equal to 2 pi I times the sum of our answers for part B, because it's just going to be the sum of the residues. We'll get 2 pi I divided by 3. Then what we do is we just do the parameterization, as I said. It's a lot of algebra, but basically you end up getting something like this. And it ends up being I times our original integral. And so what you know is then, well, if these two are equal, 2 pi I on 3 is equal to I times our integral, then, well, lo and behold, our integral will be 2 pi on 3. Cool. Yeah, this one is a bit more open-ended, and it requires a bit more thought, because we're not actually given all of the information. We're told to solve the integral from the outset. So looking at this, we've got a cos 2 pi, we've got a cos pi, sorry, not 2 pi, we've got a cos 2 theta, cos theta, and we've done the integral from minus pi to pi. And so again, it's going across an interval of 2 pi length, so most likely this will be a unit circle or some kind of circle of some sorts. So in this case, cos 2 theta and cos theta, we know we can actually express in terms of ECI theta. And that's really good because the parameterization is going to be ECI theta, I'll just write it out, gamma theta equals ECI theta, for theta lies between pi and minus pi. So if we can somehow express everything in this integral in terms of ECI theta, and also recall that whenever you take the integral, you need to add the derivative term, so I ECI theta, because the formula for a line integral is f times gamma theta, then you also multiply through by gamma prime theta. Anyway, back to this, right, looking at this, we need to somehow express everything in terms of ECI theta, and we need to somehow shove this derivative term into it. So all we do is we do that classic expansion where we've got cos theta is equal to e to the I theta minus plus e to the minus I theta divided by 2. And if you chuck all this in, actually I'll just draw it out as well. This integral is equal to, let's just write it all in terms of ECI theta. And if you do this, then yes, you can represent everything in terms of z, right? Because what happens is, before we were changing this to gamma theta. But now what we're doing is we're doing the opposite. Instead of changing z to gamma theta, which in this case is going to be e to the I theta, we change e to the I theta back to z. But also we need to somehow have the derivative term, so I times e to the I theta in there. But we don't really have it directly, so what we do generally, I'll just start a new page. So what we do generally is instead of trying to find this term in there, we force it in there. So we say we need the derivative term to be in this integral, so just divide by it. Yep, divide by it and then multiply by it. Right? So in other words, now we've got gamma prime theta in there, and we've also got everything in terms of gamma theta. So then it becomes time to change this in. So we've got z plus, it'll be z to the minus 1. All of that divided by 5 plus 2 times, oh sorry, it'll be z squared because it's cos 2 theta. Yep, this becomes z plus 1 on z. And then also you've got dz, and you'll divide by iz. And so this ends up looking really complicated, but it's definitely possible to evaluate. And so if you look at what we've done over here, it becomes just a matter of calculating all of this, and then factorizing the bottom. Because the idea is that we can't actually calculate this integral directly. What we're going to do is we're going to use residues, and that means we want to express the denominator in terms of the factors. Right, so hopefully we can see how this came about. We've just done exactly what I just did there. And we've divided by iz because iz is equal to I e to I theta. Okay, cool. And so now we've got all of the residues, and we want to calculate this integral now, because once we've gotten this integral, we can reduce it to the original one. So how do we calculate this integral? We look at where we're doing it. We're doing it on the unit circle. And we're doing this on the unit circle, and where are our singularities? Well, there's one at 0. There's one at minus a half, and there's one at 2. So really all we have to do is, because we're just doing the integral around this unit circle, we just do the sum of the residues at 0 and a half. And it becomes, you can kind of see that z equals 0 is going to be a pole of order 2 because we've got a z squared. Z equals minus a half is going to be equal to a pole of order 1 because it's just a linear term. And so we just use the formulae over here. So we multiply through, just recall the formulae for residues. You multiply by z to the n, differentiate n minus 1 times. So in this one you've just got 17 on 12. This one you've just got minus 5 on 4. And so using Cauchy's residue theorem, what you end up getting is you just got 2 by I times the sum of the residues, and then you get pi on 6. Cool. If there are any questions in the chat, just let me know. But that's how that's basically the integrals we've got done. We're going to move on to Fourier and Laplace transforms. Alrighty, so this is a topic that's not been covered in 2621 in recent years, but only this year. So Fourier transforms and Laplace transforms are basically ways we can transform functions that we've got with complex variables. So given a function in this space L1R, and L1R is just the space of integrals where the absolute value you can integrate from minus infinity to infinity. Given that this function exists and it's in this space, the Fourier transform of f, which we write as f hat, is equal to the integral from minus infinity of f of x times this thing, which is equal to e to the minus ix psi. And now what we've done is we've turned it into a function of psi. So what that basically means is we've got an integral, and the integral is in terms of psi, and then we integrate that, and we get a function of psi. So we're removing x from the equation altogether. It's now a function of this parameter, psi. The inverse of the Fourier transform is interesting because given certain conditions on the Fourier transform, because what a Fourier transform does is it transfers a function fx to another function f hat psi. Right? Given certain conditions on f, you can actually reverse it as well. So given the Fourier transform, you can successfully recover the original function. Right? And so what you've done over here is we've written a formula for it. So the conditions you need needs to be continuous and bounded, and also its absolute value needs to be integrable, like that condition we had before. Where this thing is finite. But basically, if it exists in this set, then the Fourier transform is invertible, and you can take the Fourier transform, apply this integral, divide by 2 pi, and you'll get the original function. Cool. So looking at this, we're finding the Fourier transform of a function fx. And all we really have to do is apply the formula we had. So we're going from minus infinity to infinity. You've got e to the minus 4x, absolute value, and you multiply that through by e to the minus I x psi. And so we've got this over here. And what you want to do generally with these kinds of equations with absolute values, and usually with Fourier transforms, you'll have some kind of absolute value somewhere. But what you want to do is separate this into two equations, because we can't really integrate absolute values. So do the positive side. Yep. Except this turns into 4x. Because what we're doing is we're saying the absolute value is equal to itself on the positive side. It's equal to the minus of itself on the other side. Right, and then we integrate that. You'll see it's just an exponential function, so it'll be 4 plus I psi times x dx plus 0 to minus infinity e to the 4 minus I psi x dx. And so you'll calculate both of these. You just use standard integrating techniques, and you'll end up with 8 on 16 plus psi squared. You'll actually end up with a sum of partial fractions, but you want to rationalize it, you want to realize it using the conjugate, and you get 8 on 16 plus psi squared. Moving on to a second one called Laplace transforms, which is more commonly examinable. But before we talk about Laplace transforms, we have to understand a concept called an exponential of type A function. So looking at a function fz, this should be ft. If we can somehow bound this above by some constant times e to the at, then it's going to be exponential of that type. So for example, a function like e to the 2t, we can bound that above obviously by e to the 2t. Right? So this function is going to be exponential of type 2. Right? And basically what this is saying is it's imposing a condition on growth. So it's like describing the order of growth of the function. So roughly speaking, if a function is exponential of type A, then f grows more slowly than a function in the form e to the az plus ibz, because e to the ibz doesn't really grow at all. It just kind of circles around because it's the cos plus I sine. But something like this, if it's exponential of type A, it grows more slowly than any function of the form e to the a plus ibz. So when we have a function that's exponential of type A, then what we do is we consider the half plane. This is called a half plane, HA. And this notation is important for Laplace transforms. So we draw out the complex plane. And let's just say this is A. Then this half plane is equal to the set of all numbers such that the real part is greater than A. So this thing over here. And if we have a function that's exponential of type A, then we can define the Laplace transform on this half plane HA. And so the Laplace transform is given by, and we'll look into the intuition of this HA thing in a second, but the Laplace transform is given by another integral where we integrate some function of z and then make it a function of z. So ft e to the minus zt dt. And that's the Laplace transform of f. And so the reason why we needed this condition is because think about what will happen if, say, fz is not exponential of type A. If ft is not exponential of type A, it means it might grow more quickly. It might grow very quickly. So for example, if I do like LF of 1, LF of 1 is equal to ft times e to the minus t dt. And what you'll figure out from seeing that is that this function, if this function is not exponential of type 1, for example, it'll grow more quickly than e to the t, which means this integral will just diverge, which is not what we want. So that's why we need this condition, where the real part of z is greater than a, because then we can impose the condition where the Laplace transform is defined. All right, an example with exponential of type A functions and Laplace transforms. So find the smallest real number that sine, such that sine 0 to infinity to the complex plane, is exponential of type A. And just be warned over here that sine is not going to be defined on the entire complex plane, because when we're doing Laplace transforms in this course at least, the domain is just going to be 0 to infinity. So sine looks a bit like this on the on 0 to infinity, and you want to basically find a function such that it's less than c times, we'll just write out the formula, f of t is less than c times e to the at. So what values of a would satisfy this? Well, let's just say, for example, 1, yes, it would satisfy it because it's always greater. If you just take a equals 1, that's the exponential function, it's always greater. But really, we don't need it to be that big. If we just do something like 0, it'll still bound it above, because it'll just be 1 all the entire time, and sine is always less than or equal to 1, at least on the real axis. So it does seem to be that 0 would work, but they want the smallest real number, so the question is, does any number less than 0 work? So 0 definitely works. But would any number less than 0 work? Well, no, because if we draw that out, we'll get something like this. And that will decrease as, it'll approach 0 asymptotically as you go towards infinity, which means it'll always not bound sine by above. So that's what we've just said. So sine t is less than e to the 0t, since sine is bounded above by 1. But it's not true for any s is less than 0, this should be less than 0. And so a is going to be equal to 0. And that's the reason why we did that, is because we're going to calculate the Laplace transform. And then when we calculate the Laplace transform, we want to know where it's defined. And that's going to be defined on the plane HA, where A is this exponential of type A thing. So it'll be defined on H0. So before we actually do any maths with Laplace transforms, we know this will be defined on H0, which is the set of all numbers such that R of z is greater than 0. Okay, coming back to this, so yeah, let's just calculate this. So it's just going to be the integral of this function, and you can rather simply calculate the integral of this function just by doing integration by parts. So the standard procedure with integration by parts, we'll just integrate, find the primitive of this one, then do that again, and you'll just get some kind of function of the original Laplace transform, and then you can just make it the subject, and you'll get LF equals 1 on z squared plus 1. Alrighty, so we'll go on to our last topic, which is properties of the Laplace transform and using them for differential equations. So the Laplace transform is holomorphic. And so if you actually try to differentiate it, you'll end up getting the Laplace transform of another function in terms of the original function. So you take the Laplace transform of f, and if you differentiate that, you'll get the Laplace transform of minus t times ft. And it will be defined on the same range as well, so HA. For the function gt equals e to the minus at times ft, you can write the Laplace transform of this one in terms of the Laplace transform of f. Right, so another function is lg z is equal to lf z plus a. Another useful property is when you have t, and you have another function where you actually do a linear transform of the input variable. And so that ends up being LGZ is equal to A times LF AZ. And the last property you can use, which is probably the one that comes up the most, is the Laplace transform of the derivative of f. So you've got f differentiable. Then L, the Laplace transform of the derivative, is going to be equal to this. And it looks really similar to integration by parts. That's because it comes partially from integration by parts. But it'll be equal to z times LF z minus f0. So let's do an example involving these properties. So we've got f prime, all the way up to f, the n minus 1th derivative of f. They're all continuously differentiable with Laplace transforms. Show that the Laplace transform of the next derivative is equal to this theorem over here. So you can probably imagine that because the derivatives are defined iteratively, then what you're going to do is do it by induction, because then once you've gotten the Laplace transform of, for example, n minus 1, it's easy to use this property, because this property tells you the Laplace transform of the next derivative in terms of the previous one. It's easy to use that property in order to show it by induction. The base case is pretty simple, because you sub in 0. The left-hand side just turns into the Laplace transform of the original function. The right-hand side does too. It'll be z to 0 times LF z. And then this sum is nothing as well, because you'll be summing from I equals 1 up until 0. So the base case is true. The next thing is, let's just assume that the proposition is true. So let's assume it's true for n equals k, and you've got this. And so what you're going to try to do is calculate L of f k plus 1 z in terms of all of this stuff. And so what you're going to use is, let's see if we can remember that formula. So the Laplace transform of f prime z is equal to z times the original Laplace transform minus f0. Okay, and so applying that to the kth derivative, we've got the Laplace transform of the k plus 1th derivative will be equal to z times the Laplace transform of the kth derivative minus f0. And what we'll then do is try to substitute this thing in to get the to prove the hypothesis. So I've written it out over here. We've got z times the Laplace transform of the kth derivative, and this one we just sub in, you get z to the k times the original Laplace transform minus this massive sum. And then you also subtract the kth derivative at 0. And what ends up happening is you get, because you're trying to show that this is equal to z to the k plus 1, basically you're just trying to show the proposition with k plus 1. This turns into k plus 1. And this sum, because we've got this additional term over here, turns into the k plus 1 sum. Right? Because this we multiply through, z times z to the k. And this one, each of these terms becomes multiplied by z, so you get from k minus I to k plus 1 minus I, and then you end up getting an extra term at the end to account for the missing one. Right, let's move on to our final topic called inverse Laplace transforms. So, same thing with Fourier transforms. You can calculate the Laplace transform, and you can also invert it. So once you've calculated a Laplace transform, if you want to figure out what the original function was, you can then take this integral. So I'll just draw out what the integral looks like, but it's going to be the limit, so it's exponential of type A. And we've got the Laplace transform defined on HA as well. So what you can do is, if you take any number, sigma, in this domain, and you take the limit as r approaches infinity of the integral between sigma minus IR to sigma plus IR, that's basically like the infinite integral along this vertical line. So you're taking it as it approaches infinity in both directions. And so this integral as a whole, if you take this entire integral, you get back to where you started. So it is quite nice, because with the original Laplace transform formula, I'll just show you over here. you're taking an integral of ft from 0 to infinity. And then to get back, all you need to do is just take this integral of the actual Laplace transform along the vertical axis, and you get back to the original function. Turns out this is pretty annoying to do. So if there exists this property, and we'll get into that later, but if there exists this property, then you can actually calculate this integral itself using the residues theorem, and you get this thing instead. You just get the residues of the Laplace transform times e to the zt at all of the functions that it's all of the singularities. So what is this property? It basically just says that the Laplace transform is bounded by z to the minus k for some positive constant k. And if you can show that, then you can basically use this residues theorem. One more property we need to do before we get into our final question is the Laplace transform of a convolution. So if you look at a convolution of two functions, it's actually the integral of some combination of those functions. It's the integral of fs times g times t minus s ds from 0 to t. And you'll look into this more in statistics later as well if you do statistics. But you'll find out that the convolution of two functions is given by this integral. And one useful thing about the Laplace transform of a convolution is if you've got Laplace transform of the convolution is equal to the product of the individual convolutions. Okay, so we have all the tools to solve our final equation, which is about applying them to differential equations. And so it turns out actually that all of these kinds of questions where you're doing differential equations, all you need to do is just take the Laplace transform of both sides, right? Simplify, and then somehow you'll get like LF is equal to something. And then guess what you do? You do what we just did, right? You invert the Laplace transform to find out what F is equal to. Yeah. So this is no exception. We've got an integral equation. We want to take the Laplace transform of both sides and then somehow simplify. Okay. So when you're taking the Laplace transform, it's linear, which means that you can take the Laplace transform of a sum, and it'll just be the sum of the individual Laplace transforms. So on the left-hand side, we've got LF. Right-hand side, we've got the Laplace transform of t. And then we've got plus. And look at this. This is actually a convolution. So more often than not, when you're doing the Laplace transform of an integral, it'll come down to a convolution. Because if you recall the formula for a convolution, it was from 0 to t of f of t minus s times g of s ds. And so what that means is that you've got an integral with t at the top, t at the bottom over here. So this function t minus u squared ends up being f squared. So f ends up being one of the functions. So this is a convolution of u squared and f. Right, because this f t minus s needs to correspond to t minus u. So it's just a square function. And then this one needs to correspond to this one. So we've got the convolution of f and the square function. And that's what we've got over here. We've got the Laplace transform of t mapping to t, the Laplace transform of t mapping to t squared, and then the Laplace transform of f. And you can see why this is useful, because now we've got the Laplace transform of f and a bunch of variables over here. So somehow we're going to make this the subject, the Laplace transform of f the subject, and then we'll end up calculating f itself. We know the Laplace transform of powers, right? There's a simple formula for that we can use, right? If we've got the power t to the k, you can just use k factorial divided by z to the k plus 1. So over here we've just got Laplace transform is equal to 1 plus z squared plus 1 on z cubed times LFZ. And you end up getting this. Okay, and so that's not done right because we've just found out that the Laplace transform of f is equal to something. We need to now do the inverse. And think about the function itself that we're getting. So LF is equal to z on z cubed minus 1. Does that satisfy the property where it's bounded above by the power function? So remember this property. We'll just scroll up. we need positive constants that bound the Laplace transform by m times z to the minus k. And is that the case over here? Well, yeah, because we've got a z divided by a z cubed, and so that's approximately equal to 1 on z squared. So formally speaking, we can just reduce it to z on z cubed minus 1. So we've done this before in part 1 as well. We've done a lot of this where we do circle inequalities to find bounds. But basically you can see it's bounded above by 2 times z to the power of minus 2. So we can now use the residues form of the inversion formula. And so what that means is that the Laplace transform, the function you can get by taking the sum of the residues, looking back up at this. If you can find the sum of the residues of LF times e to the zt, then you'll somehow find the original function. So what is it? Fz times e to the zt at all of the singularities. Right, so hopefully this still makes sense. We're doing the sum of the residues. Now it comes time to find the residues by finding the singularities. So z on z cubed minus 1, you can imagine we'll have 3 roots at the bottom, so we'll have 3 singularities equal to the 3 cube roots of unity. So in this case, we've just written them out, and they're all going to be simple because there are 3 separate linear terms. Okay, moving on to this. So what you can do is you can find the residues of each of these singularities. I'll just write them out. 1 e to 2 pi on 3i, e to the minus 2 pi on 3i. And so once you've got that, you can calculate the residues at each of those points, and then you'll get your answer. Okay, so just one thing to note, a very simple way of doing this is to calculate, use the P on Q prime formula. So when you've got a simple pole of a function f equals P on Q, it's actually true that the residue you can do, and you've seen this formula in class before, you can do P on Q prime, and you evaluate that z0. Right, so we're just doing that over here. We're just doing z e to the tz divided by 3z squared, which will be equal to e to the tz divided by 3z, and then we're just subbing in z0. Right, so there's a lot of calculations, but basically what you then do is you calculate the sum of the residues, which is equal to, this one is pretty simple because it's just equal to 1. You get e to the t divided by 3 times 1, which is e to the t divided by 3. But these two are a bit annoying. You end up getting two things that are the conjugate of each other. And then you can combine them to be one real part in terms of cos and sine. And you end up getting a nice sum of cos and sine at the end. And so the whole point of this is that you're just doing the residues of this function in order to get ft. And as a final sanity check, you should check that f of t is actually a normal function, like in terms of t, which in this case it is. Right, so that's how we finish off these kinds of questions. We take the Laplace transform, then we take the inverse Laplace transform to find out what f is, and you end up getting a nice solution in terms of t. Alright, so that's basically all of that done. There are obviously other types of questions for differential equations, but they all follow the same kind of process, where you take the Laplace transform of both sides and use the properties of Laplace transforms. So if there are any questions, just let me know in the chat, but that brings our seminar to a close. So we covered a lot of ground, obviously. So the main point of the course is obviously the residues theorem, where you can basically evaluate any contour integral on any contour, even if there are singularities. The Laplace transform is just an extra section that was covered this year, but hopefully you found that useful, and obviously best of luck with your exams. Hopefully you enjoyed the seminar as well and enjoyed the course. Right. Thank you all for coming.